Here we're going to talk about more topic about inverse kinematics. For direct forward kinematics, if you try to come up with the position with the given parameters, theta, alpha, A, and D, it doesn't matter how many points, how many joints you have, as long as you follow the formula, step by step, one by one, you should be able to find the final position of the robot. However, if you try to solve everything backwards, like you try to find out all the coefficients for individual joints using inverse solving procedures, you're going to find it is going to be difficult. As we talked about earlier, there is no systematic way to solve uh, the individual parameters. In particular, if you have one variable, you need to have one equation. If you have 6 joints, you might have 24 variables. It is not very likely that we can solve all the 24 variables. Though we might have some kind of restrictions or limitations for individual rotation movement or linear movement, we might be we might be able to move like 30-degree only or 90-degree only. However, if you do not have enough equations, it is very unlikely that you're going to get all the correct number of coefficients. So in this case, it means that if we have more joints, it means that we're going to have more variables, and it's going to be very tedious calculation procedures. If you only have one link, then it might be easy for you to identify all the coefficients, but if you have more than two, then it is probably not the calculation efficient. So when you have more joints, you might be still able to come up with a set of solution. However, that one is not the only solution for the configuration you try to do. Also, since we have cosine and sine involved in our system, sometimes we might have tangent term to solve for the coefficients. It means that we need to deal with a lot of nonlinear functions. When you have nonlinear functions, you cannot use the technique we learned in uh, linear algebra to solve for unknowns. We need to solve everything step by step. If you have cosine and the other question you have sine, then you might need to um, use some kind of triangular formula to come up with the answer. So everything is somewhat difficult to solve. And also, even though we are talking about the same end position of the robot, there are very likely more than one possible solution. So that is something you might need to remember. The other thing that is difficult for engineers to come up with the systematic way to solve the unknowns is because when you are having a structure, depending on the geometry shape, the solving procedures is somewhat case by case instead of a systematic approach. So those things uh, may prevent engineers to calculate the inverse kinematics of a robotic system. Everything we need to do is just try to do some analysis, try a more efficient way to design the trajectories. So that might be something we're going to talk about uh, in the next few modules. Let's do one final example. This example over here has 3 joints. They are the rotational one, this one, they have another rotational one. This one is a joint that can generate linear movement. So we have 3 links, and we need to come up with the transformation matrix. Once that is done, then we are anticipated to use inverse kinematics to identify all the coefficients at individual joints. So let's do that. So we are given 3 joints or 3 links. Okay. we need to find transformation matrix. Let's assume we just need to deal with the first part. So before we start, the first step we need to deal with this kind of problem is you need to attach a frame to the two individual joints. So since they attach x1 over here, z0 over here, so normally we are having z0, x0, y0. Okay, and for the z1 over here, clearly x1 is not changing its position, which means my coordinate of the first frame is going to be z1, x1. Now you will need to use the right hand rule to determine what is the direction of your system. It is going to be y1 because this one has been rotated for 90 degrees, which yield the y0 direction becomes y1 direction. That is something we're going to do. For this one over here, everything is pretty much specified, so just leave it like this. And this one over here is going to be z2, y2, x2. This has been rotated back to its original position. Then the rest are the same. So, okay, so let's make a table. Got E1, 2, and 3. 1, 1, 2, and 3. Since join this one and this one, they are considered to be at the same point. So that's AI, alpha I, DI, theta I. So since they are attached, the code x1, frame 0 and frame 1 are attached their position, the coordinate system onto the same points, which means the distance, the offset and distance of those two joints are going to be 0. And the first rotational joints is rotating theta 1 degree. And the and the alpha 1, that's between this frame, this axle, and this axis. Okay, so clearly we need to attach 2 pi over here. For 2 to 4, 1 to 2, it has been from this direction into another 2 pi direction. Along the axis, there is no change in terms of depth, but from the center of joint 1 to the center of the cubic, we actually have D2 listed over here. For the third one, there is no change compared to the third frame, but there is one thing changed because there is a linear movement along this direction. Then it's going to give us D3. So this finishes my table. Then let's start to build the conversion. So from this one over here, we are having the rotational multiplied by the translational. So we got that is going to give me from now on I'm going to use C theta 1 equals to cosine theta 1. Sine theta 1 equals to sine theta 2, theta 1. Okay. There's nothing changed. I just try to save the time writing down everything. For the transformation matrix of the whole thing, um, so over here we got um, the x1 y1 is actually along y1, and y1 is along negative z-axis. In y0 direction is 0, and in x0 direction is 0. For z1, it's going to be 1 here, 0 here, and 0 here. So, and okay, D is not moving anyway. So, my edge 0 to 1 after operation, it is going to be cosine theta 1 negative sine theta 1 0 0 negative 1 1. And over here, this is where is it? Sorry, this one is 0. Confuse myself. So this is the first part of rotational one in the matrix. In order to make H, this is something you're going to have for this specific R1 to R0 to 1. Okay, the rotation matrix for 1 to 2, it is going to be 0, 0, 1, 0, 0 over here because we are rotate about the axis again. So we have cosine theta 2, sine theta 2, negative sine theta 2, and cosine theta 2 for the coefficients over here. And D2, we do have some kind of a movement or offset between the first, the second joint and the third joint. So we're going to have 0, 0, D2. Combine both of them together. We all have cosine theta 2, sine theta 2, 0, negative sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, 0, 0, D2, 0. So this would be the second transformation matrix we're looking for. As to H2 to 3. This is pretty straightforward because there is no rotational movement. We do not have any linear movement. We do have linear movement. So the angle for the rotation matrix is going to be 0, which means the matrix over here is going to be an identity. So we can just put the 9 components over here. And we also mentioned that there is D3 along Z direction. The rest of the 4 components are going to be 0, 0, 0, 1. So the transformation matrix is going to be the combination of everything. This one, this one, this one, this one. 0, 0, 1, 0, 0, 0, D3, and 1. So this is going to be the matrix that we need to deal with. So if we expand the equation, the matrix is going to look like a huge one. There will be, let me put it over here, cosine theta 1, cosine theta 2, sine theta 1, cosine theta 2, negative sine theta 2, and 0. The second column over here is going to be negative sine theta 1, cosine theta 1, 0, 0. Cosine theta 1, sine theta 2, sine theta 1, sine theta 2, cosine theta 2, 0. This is going to be cosine theta 1, sine theta 2, d3, minus sine theta 1, d2. Second term is going to be sine theta 1, sine theta 2, d3, plus cosine theta 1, d2, cosine theta 2, d3, and 1 over here. So when we are calculating those kind of measures altogether, the result can be very complex. So as you can see over here, though we only have variables theta 1, theta 2, d2, and d3, we actually have 4 unknowns. But when we try to solve theta 1, theta 2, d2, and d3, sometimes it can be a little bit tedious because the cosine term and sine term, as we discussed earlier, they are not linear combination, so sometimes it can be a little bit difficult for us to generate a correct answer. And in some cases, even though we can find the answer, it might not be unique. You can always find different combinations of those coefficients so that you can still we can still have a robot stop at the same destination. Let's talk about how we're going to do that. Okay, so in order to find out the reverse problem we are going to be created to solve the inverse kinematics. Go back to the configuration over here. So if we try to figure out what's going on at the specific position using frame 1. So when we describe something using frame 1, it should be the same information you describe from other frame. So you can use the transformation matrix from frame 1 to frame 0 to frame 1. Then you get a coefficient located in frame 1. You can always use the direct configuration to come up with the answer directly from frame 1. So the coefficient, the vector should be the same. Let's talk about what we really want to do. So if I want to describe the position, let's do it this way. If let's say I'll have something this is my x1, this is actually my y1, and this is my z1. Based on the configuration in the previous slides, we conclude that based on using right-hand rule, the x1 direction must be this direction. That's the reason I have this one over here. Let me erase the solid line and redo that again. Okay, so keep in mind we have something over here, and after it has been rotated, the location is actually going to be at this position, and this one over here is theta 3. Okay, so if we project everything onto and the distance over here, that is d3. The distance over here, this is d2. Okay, so when we try to do something like this, we project this onto this y direction and get this part over here, d3 cosine sorry, this is theta 2, and we can also project that this one over here, and we conclude this one over here, that is going to be d3 sine theta 2. Does it make sense? Because we have the information theta 2, we have the information at d2 and d3. So if this is my p, visualized from this plane, it is going to be d3 sine theta 2 because it's along x1 direction, and it is going to be negative d3 cosine theta 2 The negative sign is because my positive sign is over here. So since this projection is on the other side of the axis, it must have a negative sign in front of it. And along the z direction is d2. Nothing fancy. Okay, that is something we can describe from this coordinate system in frame 1. Also, if you visualize everything from P naught, from the zeroth frame, we assume it's going to be Px, Py, and Pz. And originally, we're supposed to be able to find out everything like this, since we observe everything in the frame from the zeroth frame. And this should be something given in the problem statement. We know the end position, which is measured from zeroth frame. So when we have something like this, we would need to attach the transformation matrix from zeroth frame to this frame. We can use a technique we learned in the previous module. So the rotation matrix is going to be cosine theta 1, sine theta 1, 0, 0, 1, 0, 0, negative sine theta 1, cosine theta 1, multiplied by px, py, pz. This one over here is going to give us p1. So this is a conversion from 1, 0 to 1. Then multiplied by p naught. We're going to get p1. That it should be something we talk about in the second chapter. So if we do something like this one over here is going to be px cosine theta 1 plus py sine theta 1. Second one is going to be negative pz. Third term over here is negative px sine theta 1 plus py cosine theta 1. Let's copy it to here. So we are going to have px cosine theta 1 plus py sine theta 1 negative pz negative px sine theta 1 plus py cosine theta 1. So over here, there are a few things you might need to know what's going on, because we do not know theta 1, theta 2, and we do not know d3 as well. So, and d2. So we might need to come up with the answer about what's going on. So let's start doing it. So we are going to use some kind of technique, and this technique has nothing to do with robotics. That is, let me put it over here as a side. If you have cosine theta, that is actually 1 minus tangent square theta. In the denominator is 1 plus tangent square theta. No, 1/2. And sine theta is actually 2 tangent theta over 2 1 plus this one. Okay, so let's explain this one a little bit more. So if we have tangent t theta over 2 equals to t, then cosine theta is going to be 1 minus t squared, 1 plus t squared. Sine theta is going to be 2t over 1 plus t squared. Okay, so those triangular formula is going to help us to solve the answer. Over here, we have three equations because keep in mind we are talking about P1. So this component over here must be identical to the numerical answer over here. Second one is going to be the same, third one is going to be the same. So if we want to solve this kind of problem, let's start from D2, which means I'm looking for solving D2 equals to Px sine theta 1 plus Py cosine theta 1. Okay, so since we're out of space, so I'm going to write it down over here. I'll have D2 equals to negative Px sine theta 1 plus Py cosine theta 1. Okay. So what I would need to do is to assume tangent theta 1 over 2 equals to t. So when we do this, we are actually having d2 equals to negative px 2t 1 plus t squared plus py 1 minus t squared 1 plus t squared. This term and this term are something we have on the previous slides. So putting everything all together, we are going to have okay. So you might be able to visualize. Okay, now I have variable t. So if I have variable t, can I put all the numbers together to synthesize a quadratic equation? What I mean is I have t squared. The coefficient is going to be d2 plus py. I have, well, maybe it's better visualization to do something like this. So for the first order term, I'll have px 2t. I'll have the constant term over here is going to be d2 minus py equals to 0. Since this one is quadratic equation, we should be able to solve for t using the formula. So if we use the formula, then we're going to get my t equals to negative px plus minus px squared plus py squared minus d2 squared. The denominator over here is going to be d2 plus py. Okay, once t is solved, what can we do? Go back to the previous slide. Once t is solved, we got tangent theta over 2, and if t is derived, we should be able to find out cosine theta and sine theta. So with this equation over here, theta is going to be, oh, let me put it over here. So what I'm going to do is repeat the equation I have. So keep in mind when you are solving this kind of problem, you might notice that the angle might be plus minus. You might have two answers. That's correct because again, we are not solving for a unique solution. We are solving for different solutions. And this is theta over 2. So you need to have 2 over here. And this is, of course, theta 1. So that completes how we solve for theta 1. And once theta 1 is solved, we can use this equation, I guess. We can actually use this one and combine this one together. So we are going to have d3 square psi theta 3 square plus d3 square cosine theta 3 square. That is going to be equals to px cosine theta 1 square this square plus this square. So sorry, I shouldn't have square over here. Let me erase this line, it looks a little bit weird. So this one is going to be px cosine theta 1 plus py sine theta 1 square plus pz square. This part over here, since I have sine square and cosine square, add them together is going to be 1. So d3 square equals to this one, which yields d3 equals to the square root of px cosine theta 1 plus py sine theta 1 square plus pz square. Take the square root of this combination, we actually get d3. Then we still have one more coefficient we need to solve. So I'm going to use this one and this one again. And this time we're going to use division instead of adding them together. So I'll have d3 sine theta 2 d3 cosine theta 2. I'm going to remove both negative sign because negative can be cancelled out. So over here, since I'm using this coefficient divided by this coefficient, the other side I'll have is px cosine theta 1 plus py sine theta 1 over pz. Again, px, py, and pz, they are the coefficient, they are the position measured from zeroth frame, and those information should be given in the beginning of problem statement. Once this is done, d3 can be cancelled, and this term over here is actually tangent theta 2. So theta 2 is going to be arctangent px cosine theta 1 plus py sine theta 1 over PC. Okay, my answer start from here. I solve for my theta 1, I solve for my theta 2, and also I got my D3. Okay, this kind of equation might be a little bit different because theta 1 over here can be one or two answers. We got positive and negative sign over here. So once you get the answer over here, you should get a pair, not only one. Plug this one into those two solutions, you should be able to get D3 and theta 2 located at different position. So when you are doing those kind of things, you can see, just like what we talked about earlier, there is no systematic approach to solve for the answer. Everything is based on geometry, configuration, and how are you going to interpret the configuration with correct geometry equations. So once that's done, then you can start to do everything required to solve for theta, d, a, and alpha. But sometimes, well, not only sometimes, in many cases, it's not so straightforward or not so easy to visualize what you need to do. This problem over here, this one over here, is something you might have problem to come up with. So when you solve this problem, this kind of problem, inverse kinematics, just be patient and use all the tools you can have to find out all the coefficients. If you can find a unique, if you can find one solution, sometimes it's good enough. But if you need to make sure your robot is following specific trajectory, for instance, if you have a robot getting a pen and drawing something on a piece of paper, then the trajectory of this thing is defined. You might be able to solve all the positions based on the configuration I'm just telling you. But just like what we discussed earlier, you might have different solutions for every position you want to do. When you have something like this, keep in mind a robot is a continuous system, it's not discrete type, which means current position must be linked to the previous position. You cannot say, okay, my robot is like this one, but before this moment, it is actually this one. Yes, configuration-wise, it's possible, but in realistic, this might not be feasible because all of a sudden, you want this position jump from this, you want this joint jump from this position into this position. You might have some kind of vibration problem, or it's totally impossible. So when you are designing the trajectories, you need to be careful, use the correct explanation and correct configuration so that individual joints can be derived accordingly. Okay, this is a solution this is an example that I want to show you. We can start from the beginning and get the final answer, and we can also use the measurement to recover individual coefficients at the joints.